We're back with AMD Extreme Overclocker and engineer Bill Alverson, and this time he brought a box full of secret gadgets that people normally don't get to see.
I took the temperature from like negative 196 all the way up to 115 degrees Celsius and then back. So 300 degree swing basically 300 times. Here it's saying that this particular stick that you loaned me is not actually write protected, okay? So this can be written to very easily. Even in a live system, you could create a situation where the SBD could be written to. So here's the EXPO profile, and so you can see EXPO ID string. It has two, at least two, maybe three I2C connectors on it, and that's how I'm interfacing with the board. So you can change CPU registers and something like this.
But for all the technicals, Bill, as always, also brought some great stories.
We had one of the board designers, Dave, was in my lab, and I don't know what Dave was doing in my lab, but but there he was. And the thing was, we were giving a tour to Lisa Sue and her family. So, and Dave presses the button and the whole thing.
And we'll put that full story at the very end of the video. In this video, we'll see how to program RAM timings physically into the stick, learn about AMD's below-the-surface BIOS options, and see some of the engineering behind building performance CPUs. Let's get into this technical deep dive and show and tell of cool hardware. All right, so I'm joined by Bill Alverson. Bill, the last time we did a video like this was in your lab.
That's right.
Yeah, so we've got a Bill's box of oddities. Bill, do you want to run through some of the cool stuff we're going to look at today?
So I brought a tray of mostly 9800 X3Ds. And these are some of the exact ones that we use to do a lot of the development work on 9800 X3D so we could bring overclocking to X3D for the first time. So I did stuff like this guy, number 3, has more than 300 therm trips on it, where I took the temperature from like negative 196 all the way up to 115 degrees Celsius and then back. So 300 degree swing basically 300 times. We brought a reference platform. We've talked about this before on one of the other videos. That was an earlier revision. This is a Rev V that I use for memory tuning purposes.
Lots of 7 segments. You have some switches over here too we can get into a little later, yeah.
We talked about this before, but we didn't really demonstrate it. This is a UDEM programmer. Actually, I can program SODEMs as well, so I can read the SPD and some other things about the modules, and I can even reprogram modules, make custom modules. We brought a EVC2.
Yeah, from Elmore.
Elmore Lab. That can interface with the board, and we can do voltage control and look at telemetry and stuff like that. And then I brought the Founders Edition tape as well, so you never know.
Well, it's been pretty important for the lab. So
yes.
You bench 67, 68, 69, and so forth.
Yeah, this is 68 right here.
Yeah. Before that, this video is brought to you by the Thermaltake TR100 Portable Mini ITX case. The TR100 case has a mesh ventilated front panel, heavily perforated side and top panels, and claims to support up to 280mm liquid coolers and large GPUs up to 360mm long and 70mm thick. It even has an optional suitcase with cutouts for the system, a mouse, keyboard, and monitor for transport. The Thermaltake TR100 Mini ITX case targets portable, smaller form factor PC building while maintaining compatibility for relatively large components. Learn more at the link in the description below. Do you want to start with the memory thing, or do you want to start with the board and the BIOS?
So we're in the BIOS now.
Okay.
We can go there.
Yeah.
So, so like I said, this is our reference platform, and this hasn't really been seen too widely. This is what our BIOS looks like on the reference platform, the way that we make it. So we take our Giza and expose all the stuff that we have, and then ODM, you know, takes that Giza and they build their BIOS with, you know, maybe fancy graphics, and then they pick and choose which features and options and stuff that they want to leave in or omit.
We should define the, so first of all, a Giza or a Giza?
I call it a Giza.
GIF or GIF?
GIF.
Okay.
Yeah.
You say a Giza, but you say GIF.
Correct. Sorry.
We'll cut that, yeah. That's not acceptable. What is a Giza?
Basically, it is a modular package that contains pre-compiled binaries that come from AMD, so maybe some source code and stuff that's proprietary, and we have different firmware blobs that are in there. And then It also has components that are customizable by the ODM, allow stuff like graphics and changing the layout and stuff like that, right? So they take the Agiza and then build their BIOS with it.
Right.
So,
and so then the menus that people see in their actual BIOS on the finalized board, some of those are basically the AMD provided menus, right?
Right, and you'll probably recognize some of that here, yeah.
Right.
So there is a notion of generic AMD settings, and that mostly encompasses like CBS and the overclocking menu. And then there's platform-specific stuff like some of this stuff, or another menu here, the PBS menu.
Yeah.
And you do see this on ODM boards, but it'll be it'll be configured specifically for their board and may not.
Some of these I don't
know
if I recognize. I don't think I remember seeing MIT and WIT before.
I don't even know for sure what is that. And there's absolutely brilliant help text to help us, but they're currently both disabled.
Right, that's good. We don't want those.
And then like this, right? L1
Yeah,
substates for PCI Express, but most of the motherboard like that you buy at retail, they don't even route the wires that you would need to support that to a PCI lane. That basically allows you to power gate a PCI device that you have, like an NVMe drive.
Okay.
Very important for mobile because the NVMe drive is idle like 99% of the time, so you just turn it off.
So if there's extra options in here that aren't normally surfaced, do the ODMs have the option to turn them on?
Yeah.
Okay.
Yeah, and you know, something like that, an OEM like HP or somebody like that, they're gonna possibly need to adhere to like Energy Star and stuff like that.
Okay.
So they may include that feature.
Right. I think the read I have on the community at large is if it's in BIOS, then it's the person whose name is on the motherboard that fully controls that thing. But how much does AMD sort of prepackage stuff and say, you know, this is the feature to insert versus how much are the board vendors going off and doing their own stuff? So I mean, like, for example, the overclocking, there typically are kind of duplicate options, right? So how does that play? Does one prevail over the other?
Yeah, okay, so, you know, a while back, this used to be way worse. We had triplicate and even quadruplet entries in the BIOS. So when we go do the motherboard overclocking and, you know, readiness workshops in Taiwan with the motherboard ODMs before, you know, a launch of a new CPU, that's one of the things that we go over, right? And you know, we try to reduce it down so that only maybe some options are duplicated, but not in triplicate or more.
Right.
Now, as far as which setting takes precedent, that is the setting that you change. Okay. And it doesn't matter who owns it. Okay. Right? And if there's a different behavior than that, then it's broken. Right. So that's the guidance that we give them. So if they have some setting for memory overclocking in their menu, but they still left it exposed in the OC menu that we provide, then whichever one is used takes precedence. Okay.
Is there anything in this version of the BIOS that you think is particularly, you know, worth showing people? Because it's a little different. So
this is a special BIOS because this is an internal version. So it's going to actually show debug options. So you can see that every menu is in duplicate. So we have the common. And that is what is exposed in the public Agiza that we give to the motherboard vendors.
The common?
Yeah, the common. And so sometimes it's actually still worded that way. And that's why, because we have a debug menu for most of those.
Can we look at CPU common?
Yeah, so
these I recognize most of.
Yeah, and you know, like I think Asus tends to leave all this in there for like this particular menu, but some others clean it out. Some others, they also have the option, if they don't like the way that we've grouped together stuff, they might group together things in a different way and put it in a different menu or something like that. And then they may remove it from here in that case. This is the native OC menu. So a lot of the boards ship like this, right? But this is a common one they like to remove because they may not actually control voltages in the exact same way that we do. And so they may omit this or maybe just leave this part up here.
What are the different options for controlling voltages?
Okay, well, Threadripper is the best example. Okay, so Storm Peak. Actually, in our guidance, as I understand it, we didn't, in our reference platform, rather, we didn't make a way to control the VDDIO voltage. It's actually called VDD11S3.
Okay.
And so it's been mislabeled in the Storm Peak BIOS this whole time, and because they just copy and pasted it from here.
Right.
But for that particular voltage, we didn't really have a way to control it. That wasn't part of the plan. So our guidance to the motherboard ODMs was like, hey, if you're going to support memory overclocking, then you need to have a controllable and programmable voltage regulator for that particular rail.
Okay.
Right? And so then they implement it however they choose to implement it, which could be different. And then, so this setting would do nothing in that case,
okay.
right?
Yeah.
Yeah.
On the memory stuff, if we talk about this program, or is it accurate to call this a programmer or no?
Yeah.
Okay. So we talk about the UDIM programmer. First of all, this was Elmore, right?
Yeah.
If I remember correctly, yeah,
That's
his
right.
logo's down there. For anyone who wants to check out his stuff, we use it in our testing all the time. So what's the story with it? Like, I mean, because we only talked about it a little bit in the lab tour, and I think the most we really got into was I kind of use it for debug and like EXPO.
Sure. I mean, I can demonstrate it.
Yeah, that'd
sure.
be great.
And I think I already said before, this would allow you to plug a
UDIM.
SODIM into
SODIM,
the UDIM, and then I can program laptop memory, which is also a thing that we support.
What's the physical layout? So there's 3 switches on it. What are those?
So those have to do with, this is the power button here, actually.
Okay.
But then there's a version of this that has 8 slots on it that G-Skill has. And these control some aspects of stuff that this doesn't support or I don't use. Right, everything is handled in software. Okay, so I've got it powered on, and it recognizes the module. Here it's saying that this particular stick that you loaned me is not actually write protected. Okay, so this can be written to very easily. Even in a live system, you could create a situation where the SPD could be written to. I assume these were given to you directly by Lexar or something like that?
I think so.
Okay. Yeah, because they wouldn't productize it with the Open SPD, not in this configuration.
Well,
I can actually
I'm
show.
sorry, Lexar, for the email you're going to get from Bill.
Oh, God. Well, I work with them too.
Yeah.
And, so sometimes we request ones that aren't locked, but actually this software can unlock it even if it is locked.
Okay.
Right?
Well, let's take it back a step. Locked versus unlocked, what is it you're talking about? What is locked?
So the SPD is divided into segments called blocks, okay? And so it's possible to choose which blocks that you want to lock, right? So a typical DIMM might have all of them blocked, or maybe like, 0 through 9, because there's also the notion of user space in the SPD. So you could actually lock all of the normal space where you have the JEDEC profile and all that kind of stuff, the brand name and stuff like that.
So are these blocks where XMP, EXPO, JEDEC, that stuff
all
is
that
stored?
Stuff. Yeah.
Okay.
So if it had write protection, I could undo it, or if I wanted to secure the stick, I could do that. So on AM5, this probably isn't a problem, right? But on Threadripper, we read DIMM temperature telemetry constantly, so we're polling the DIMM for temperature data, however many DIMMs you have populated, right?
Right.
So if you try to use CPU-Z or hardware info or something like this, that's going to go out on the I2C bus and go try to talk to the SPD chip on the memory, and then you have this other traffic, then you do end up having some kind of collision and malformed traffic. And what we saw was that it would reliably corrupt all of the SPDs present on the system.
Okay.
Right? And then you could refresh CPU-Z or whatever tool, and every time it would have new junk data showed for the SPD.
Okay.
And then you go to reboot the system, and it doesn't detect modules anymore, and it just beeps at you. Right?
Got it.
So yeah, the solution was those software vendors, we give them instructions on how to actually disable the DIMM telemetry.
Okay.
And then they disable it, they read all the SPDs, and then they re-enable that telemetry.
What's kind of the path for how these things communicate to each other? So where does I2C get used? What is SPD controlling, just to break down the top level?
Yeah, so the SPD is the main thing that we're trying to either read or program here. It's serial presence detect is what that means, and it's basically a very tiny EEPROM.
Okay.
Right, so electronically erasable, reprogrammable. It's not, I don't think it's flash, I think it's an EEPROM, and it's something on the order of like 1 kilobyte of total space. That's all it has.
Yeah.
So
and that just stores basically profiles and timings?
Yeah.
Okay.
Yeah, and all that stuff is encoded per JEDEC specification that talks about how to encode those data for maximal efficiency, so that these profiles, they're not just a bunch of discrete numbers like CL32 and all that, right? They're all encoded in reference to time.
And then I2C, where does that come into play?
Yeah, so a lot of motherboards you buy even expose headers that touch the I2C bus, but the memory sticks are connected to it, so every single slot. And actually, if you have memory sticks with RGB and you use software, that's going to talk on the I2C bus in your system to interface with those, right? Which could be a problem on Threadripper if you don't disable your DIMM telemetry, right? So that's why there's no RGB RDIMMs.
For the memory programming, I mean, we've kind of gone through the basics, but what is it you're actually programming? When you're using it in the lab, what's your kind of real world use case?
Okay, so I mean, when we were developing EXPO modules didn't exist yet, right? Grant Lee wrote up a spec, and but we didn't have an easy way to program modules. The original plan was that we were actually going to program them in board, but the BIOS support to let us do that wasn't ready in time. So I reached out to Jan. Because there are SPD programmers available on the market, but they're pretty expensive, low volume, and I just happened to talk to him about it and found out that he had done this for G-Skill, and he asked G-Skill if he would be able to sell them to me, and that's how I ended up with them, right? And so we were able to prototype the first EXPO modules. Because I need a real EXPO module to see how the BIOS support behaves, right? Make sure I can decode the profiles and stuff like that.
So then if you want to change the timings that are written on a stick, I guess you're able to do that.
Sure, yeah. I mean, I can kind of demonstrate it here. So connected to it, and then I read from the DIMM, and then here's all the data that it pulled. So there's the raw form of the data here, and then the software, what's nice about it is it decodes it, right?
Cool.
So I know it's a rich text.
So is that Elmore software?
Yeah.
Oh, wow.
This is all
That's
Elmore.
cool.
He's using some open source like text and hex editing. So here's the EXPO profile, and so you can see we have EXPO ID string. And so the way that works is the memory code ABL just looks at the SPD for that string, and then if it finds that string, it knows that after that, at certain offset, all the components of an EXPO profile should be there. Right? So therefore,
So is it like marking where it starts, basically?
Yeah, and this is like the suggested location, but you can put it anywhere, right?
Okay, is there a reason they choose one area versus another?
We tried to just put it towards the end, but we gave the module vendors flexibility because they asked for flexibility with it, so they can have compatibility with other technologies.
Right.
Then the other thing is the version. So this is a 1.0, version stick. We have 1.1 on the market right now as well. So that allows us to decode it properly. There's the frequency right there. That'll round down to 6,000 with the ABL code interpreting that. And then there's the timings.
So what's the EVC here for? Because that one, I actually do have an EVC too, and the stuff we've used it for historically has been external voltage control, obviously, but then we've also used his flash programmer for stuff.
So I've been using these since like the X370 days or whatever, right? That was the infancy of the overclocking, program. So we had very, very minimal to no BIOS support for a lot of stuff. Not only that, but the BIOS support that we did have was quite limited. So it wasn't possible to do anything resembling XOC or anything like that on our reference platform at that time, given all that support. Then in comes the EVC2. We can unlock the voltage, so now we can go to like 2.6 volts, right? Because that's what you need to do. It has at least two, maybe three I2C connectors on it, and that's how I'm interfacing with the board. We have two I2C interfaces exposed on the board, at least that I'm aware of, and this particular one that I'm connected to connects to the VRM controllers, and it also connects to the memory as well. In fact, I can demonstrate that.
Yeah, that would be cool. So what are these three buttons you have here? You just pressed one of them.
Oh, those are just the power reset and warm reset.
Okay,
so we have cold reset, but we also have warm reset, right? So you can change CPU registers and something like this and retain those settings while resetting the board.
Okay.
Right? Yeah, so I could actually program, for example, a voltage, and even that's outside of what I just described, but I could program a voltage and then hit warm reset and it'll retain that voltage. Cold reset and it won't.
Cool.
So I've got it hooked up now.
Yeah.
We're plugged in, and I'll demonstrate a beep. So usually when you have this plugged in to the I2C bus and you turn it on, it kind of pulls the bus down low and it doesn't reliably read the SPD. The reason it probably worked is because I only have one stick plugged in.
Do you want to get the other one in there?
Oh, they put the sticker on backwards too. So normally the sticker faces towards the socket, and they're not the first ones that I've encountered to do that.
The email going to Lexar is getting longer.
They're a good partner.
Dear Lexar,
No, they're a good
not
partner.
only was your sticker backwards.
They've sent us some. There we go.
Cool.
So
Okay, that's what you wanted, right?
Yeah. So it says E310 for at least the last 4.
On your
And
massive display.
Yeah. That says no memory.
Okay,
Right?
got it.
So if I unplug that and hit the cold reset again, then it'll boot right up. And then once it gets through that phase, I can actually plug this back in.
So you talked about them basically just, are they both occupying the same bus space?
Yeah.
And it's causing a problem?
They're literally on the same wire.
Okay,
Yeah.
all right.
I already pre-configured this. So in the software, you can click here on I2C1 is what we're plugged into, and you can see it supports 2 and 3, right? And then I select a profile for my voltage regulator,
Yeah.
and it's got a list of them from
Okay.
different vendors and stuff.
Cool.
Okay, and then once you do that, you can actually hit Find Devices, all right? And now these are all of the I2C bus devices that it sees.
So what's it see here?
Sees stuff on 0C, 0E. I mean, who knows what all that stuff is,
Right.
right? But I happen to know that that VRM controller is at address 74.
Okay.
So I select that, right, and hit Add. So here in a moment, we'll have menus that it might be different from a different VRM vendor, but you'll
Right.
find stuff like, OCP. You can even adjust how aggressive in terms of time, how fast or slow it reacts to an overcurrent event. Yeah, there we go. So it's divided. This particular controller has what we call loops. It's got 2 loops. So this first loop is actually the CPU, and the second one is the SOC voltage rail.
Oh, cool. Okay.
Right? So now if I hit monitoring, we should have telemetry. The CPU is here, and so we can watch it. It's going idle, it's going active.
Your system's actually live now too, so
Yeah.
if you were to do stuff with it, we might
Yeah,
see
we can do that
modulation, I guess.
easily.
Do you, so when you're doing bring up and early testing before the product launches, what are the reasons you might want to hook in like this with EVC2? I mean, what sort of, is it used in bring up? Are you trying to test for voltages, stability?
So this gives us easy capability where one person on a bench with a cheap tool is enabled for some stuff, and all the way to $500,000 worth
Right.
of
Yeah,
So,
cool.
but yeah, like I said, in the early days on X370 in particular, right? So I would use this guy to change the voltage here.
Yeah,
And then here's OCP set for 30 amps, right? So I can manipulate that if I need to. And then, like I said, it's got the notion of fast and slow OCP. And you can see it's set at about 1.2 volts
Right.
steady there, right? And so I can see power consumption if I run this little built-in tool in Windows. Let's see here, loop 1, output power. So that's a single-threaded workload right now, approximately. So it's only 13 watts or so, but here in a second, I think it does a multi-core run, and it'll go up to like 100 watts or whatever it is, right? So, and so we can pump this out into a file, CSV, and plot this, however we want.
Understand the
in
behavior,
post-process, yeah.
Well, this board, I guess, slightly changing the topic, but this was the one that had the socketable. You had like the stacked chipsets,
That's
right?
right.
When we were in the lab.
Yeah, it's the same exact board. This is just a newer revision of the board where we did some tweaks to get a little bit better I/O and memory signal integrity.
The story with the swappable display out.
It's kind of similar to the chipset, right? Because not everybody needs to have video out. You can see I'm using a video card, so you can optionally have that unpopulated. But we also, this is DP, we have HDMI, and we have like LVDS for a flat panel as well, and they're all plug into the same thing. So whatever output you need, you can get.
Cool. I feel like that should just be an actual feature. Asus could sell DLC everyone would be happy. I mean, you get all the ports, they get more money. It'd be perfect. I think the only thing I wanted to really ask with the one that you have in there is what, if it's quick to demonstrate your process for binning when you're looking at, I don't know, like low range of voltage or.
Sure. Yeah, that's simple enough, right? So we can do that really quick.
Yeah, sure.
We bin for kind of two things. So the first thing we usually do is bin for frequency, and we look at like maybe 1 or 2 fixed frequency points, and then and what's the minimum voltage you can run stably. And like, so we'll do something that'll kind of ramp the temperature up. So like usually run Cinebench like 3 times back to back. And if it can make it through all 3, then we lower the voltage some more and try again, just kind of iterate through that is all it is. Like I said, we might do that for 2 different frequency points, and therefore 2 different kind of ranges of voltage. And then once we find some parts that look interesting, then we go and take those and bin them for cold bugs. Right?
Okay.
So we try to figure out which ones are inherently more stable cold, and which ones are not so much, and which ones are tweakable using stuff like the VDD G voltage control and stuff like that. So the concept, like I said, is easy enough. So we can say like, we might do like 4 gigahertz and 5 gigahertz or something like that. So like just say 4. Okay, I know that like 1.1, like that's like plenty. So I don't think I expect a problem here. I'm not familiar with this exact part perhaps, but this is so much faster on Threadripper too.
Do you have, while it's running, I mean, so you had mentioned like XOC number 3 had been therm tripped a couple hundred times or something?
Yeah,
200-300 times?
Yeah.
Any stories for the other ones you have here?
They're just identified for binning. Yeah, whenever I was binning, I had a few trays like this, and we were binning them for minimum voltage and cold bugs and stuff like that. Normally, we would run this 3 times back to back, right? And then, you know, we'll go down some amount, or even a binary search maybe if we're just trying to figure out like what the range might be.
Okay.
On a new CPU, like but a new CPU on a brand new process, right? Rather than going down in little baby increments, maybe just take it down until I crash it.
Oh, got it. Okay.
And then
I see.
Yeah. So. But yeah, so that looks stable probably too, and you know, and you don't have to use Cinebench. There's other stuff you could use, whatever. Cinebench is good because if you do this correctly and you don't just go in a major increment and totally crash the system. If you're just getting close to instability, Cinebench tends to throw a software error. It doesn't take your whole system down.
That's normally
so that's one reason that we use it. And then, yeah, like the first run usually work, and then the second one, you know, and it's starting to heat up, and by the third one, you know, you're in a whole different temperature range, right? And so your voltage requirement as you're hotter goes up, right? And so if we can pass 3 times,
then you're good. You move to the next one. Last question I have for you is, what's the story to the shirt?
Which shirt?
That one.
This one? So,
the back does say,
oh yeah.
I don't know if we got the back yet.
The code name for Zen 5, the cores themselves, is Nirvana. So that's where that came from. And then the concept started with like a little yoga guy in a pose with the LN2 and the torch for extreme overclocking, right? And then when we had that idea, like, okay, someone said, okay, do a X3D stack for the yoga mat.
Cool, yeah.
So we got X3D, so.
Yeah, unfortunately, you can't buy the legally distinct shirts that AMD continues to make for the OC team. Last time it was one that said Cowabunga on the back.
Yeah.
And you can put that together yourself, but that was not available, and there's always a demand for it. So I'll just address it now. Unfortunately, you just have to become an extreme overclocker and befriend AMD.
That was the front of the previous
shirt.
shirt.
There you go. Yeah. Oh yeah, perfect. There it is. We might be able to distribute some of these through maybe like a Crandon e-waste fundraiser type thing or something, so everyone keep an eye on that. But all right, cool. I like the walkthrough. The memory section was very educational, so thanks for doing that.
Sure.
And as always, you should check out our lab tour with Bill previously. I'll link that below. It's all of this and a lot more. So, Bill, thank you.
Yep, thanks. Awesome.
We'll see you all next time.
We can unlock the voltage, so now we can go to like 2.6 volts, right? Because that's what you need to do.
Is that why there was the sad face on the CPU in your lab?
There
or is
might
that a different voltage?
No. I might have that one. So this did happen. So in those early days, on that early reference platform, we were doing XOC enabled by the EVC, and we had one of the board designers, Dave, was in my lab, and I don't know what Dave was doing in my lab, but but there he was. And the thing was, we were giving a tour to Lisa Sue and her family. So like her nieces and stuff were there. There's 3 or 4 people with Lisa, and so the thing was, in those early days, the software tool that we were using had a little glitch, and if you weren't very careful, it would default to maximum voltage, 2.6 volts, right? And so we're showing Lisa, extreme overclocking, and we got the liquid nitrogen going, and all her kids are there, and all this stuff. And Dave presses the button, and the whole thing, never to power on again. So that was my first dead CPU, I think. Right there. And I didn't even kill it.
Right.
So
was Lisa impressed?
She wasn't upset.
That's
so
good.
It went smooth.
No, that's great.
Yeah, she just kind of laughed. I think she just thought, stuff happens.